So there is no south star. Is that what all of you guys said?
Yeah. What is it?
Oh, there is no apparently that this question was south star. I don't even remember.
Not to
Yes
the,
and no. Okay, some of them say yes and no. Do we have a south star?
Not exactly like the North Star.
So what's the difference?
It's dimmer.
It's dimmer, okay,
Yeah.
but there is a star, right at the
about a degree off.
about a degree of. Okay. And how much off is North Star?
I think that one's less than a degree, but I didn't get the exact.
I'm just curious.
I was more looking at the magnitude. Though they say that that in 1,000 years that the North Star might be the South Star because of that everything will shift.
Right. Yeah. But it doesn't shift so precisely, it keeps drifting away, and it has been drifting away. That's why I asked, I think I was curious, is it really pointing in that direction? Because it's approximately in that direction. Because in the 11,000 years it has moved sufficiently, but maybe in the last 2,000 years it's not significantly moved. But it, to my knowledge, it does move significantly. It's a, like, yeah, but I never put a number to it. So, I think, what's the period? Because astronomy is how much, 4,000 year old, isn't that correct?
I think older.
Older, 6,000?
Precession.
How old is astronomy? Like, let's say, return astronomy.
Because sailing has been this ancient,
Okay.
right? So I don't know. That's
So what's the number you would put? Put in a number.
I don't know.
Not 20,000, right?
Right.
Like 10,000 is agriculture,
Yeah.
correct? So 6,000, that's why I put a vague number of 6,000. I don't know.
Okay. Yeah.
Because 4,000 BC, we surely have written clear documents on it. So I was putting 2,000 over, but we cannot go 10,000 because that's agriculture. Probably we were not that smart during when we moved, climbed down the trees. So maybe 7, 8 if you. But then, yeah, my point was that if astronomy is that old and like if the North Star is wobbling around with a period of 10,000 or something, so their North Star must be very different from our, from very different location. So that's a significant error. And we do hear about astrology having a lot of astrology in the sense that they use some stars, whatever their theme is, but they do have stars which are very well located. And they do have moved significantly. So the predictions are off from, even if assuming that the prediction is correct. Okay.
I actually had a student drop in astronomy class because they thought it was astrology. That was the reason on the sheet that I had to sign.
Oh, okay. Finish this slide. Homework. 9 that's due today. Or we said everything is relaxed, but I still have deadlines. You guys have the freedom to be responsible. Okay, so this is next.
Did you post this one?
Yes, I did post one. I think late, very late night. That'll be probably, so that's 19. It depends, there might be one more homework for sure. Maybe 2 more, I'm not sure. Okay. Probably that'll be Tuesday, and then maybe I will decide one more. Final exam. Do you guys prefer midterm 3 like exams or midterm 2 like exams?
We only had midterm 1 and 2.
Sorry, I keep thinking of the of the undergraduate. Midterm 2 like exams or midterm 1 like exams?
Take home and in class.
Yeah.
I think whatever is before the midterm, the second midterm, you can take home, and after that in class.
I didn't get it.
Before the second midterm, make it take home like the last exam, and after that, you can do it in class.
So you
After
said
that,
help me.
Maybe something.
You said like the exam will be comprehensive, right? More weighted
Correct.
after midterm 2 and less weighted for midterm.
Oh, that's what Darian is saying. So the whatever concepts are covered after midterm 3, we make it
In class.
in class.
Maybe something like the math methods last semester.
Isn't it the other way that should be done? Because the whole idea is to make you guys study the whole course, right? Right. Isn't that the idea of comprehensive? So make the simpler exam comprehensive one in class. And the take home part is for covering syllabus in a sense, right? Like I can cover a syllabus based on the homework. Think about it. They don't have to answer now. Anyone else has any comments? William? Abdullah?
So if it's like take home, when will we submit the take home part?
The deadline will be the exam. Whenever the exam ends, that has to be the deadline.
So like May 6th,
Yeah, May 6th, 12:15.
10:15.
Yeah, that's how I go. Yeah. It's a little more flexible than that, but yeah, that will be the deadline. Anything specific you guys have to say? Luke? Okay, think about it. I haven't decided anything on it. So this is just for you guys to ponder on simple decisions. Okay. We started working on the Kepler problem. We pretty much had an equation where we can get the orbit in a few more steps, and then we said, okay, we sort of solving further, started analyzing what different kinds of orbits are available in the Kepler problem. So I mean, the price is that now I have to go through a little bit so that we all refresh, including myself. I don't remember the variables that I introduced. So the idea is you're working on Kepler problem. And by Kepler problem, as I mentioned a few minutes back, it doesn't necessarily mean that it has to be a planet and a sun, right? Any interaction 1/r with which is attractive satisfies this. All the equations will remain the same. Classic example is hydrogen atom before the quantum analysis. Like there is a step somewhere where you start introducing the uncertainty principle, but until then, it is all classical. So you can call it the classical hydrogen atom, where an electron is actually going around the proton, and it will have exactly the same equation. Orbit equation has to be exactly the same, because it's just a matter of changing the constants. Scale is different. So we are talking about two masses, M1 and M2. experiencing potential energy. So let me say Lagrangian R1, R2. So that's R1, that's R2, some with respect to some origin somewhere else. And there is velocity R1 over dt. So that's the two velocities. And in general, there could be time dependence also, but in this problem, we do not have any time dependence. The Lagrangian is the kinetic energy of the first mass plus the kinetic energy of the second mass, and minus the potential energy. Potential energy already has a minus sign because it is an attractive force. So this becomes plus. As I said earlier, if it was a classical hydrogen atom, a classical hydrogen atom is not classical, so in that sense it's very different. This will be 1 over 4 pi epsilon naught times Q1 times Q2, except for that, that doesn't change. And in your homework, to realize that, oh, this is just an interchange of these constants, you use the letter alpha there. And alpha there, to my knowledge, is nothing to do with, there is an important constant, which is called the fine structure constant, which is also represented by alpha, but that's not the alpha that I use in that problem. It's just a parameter. Alpha. We changed our coordinates, the center of mass coordinates, M1, R1 plus M2, R2 over M1 plus M2. The relative coordinates, R1 minus R2. And also M is equal to M1 plus M2. And a reduced mass, 1 over mu, 1 over M1 plus 1 over M2. Because it is reduced, the lighter mass is more important. In terms of this, already there is no time dependence, so that goes away right there itself. If you change your coordinates, the Lagrangian becomes in terms of R, relative coordinates, center of mass coordinate, relative coordinates, the velocity of the center of mass, and the relative velocity of the two objects. And this comes out to be half m dr by dt, this velocity comes in, plus half mu by dt square, and the same. Oh, this should be R1 minus R2 minus. At this stage, there is no R1, R itself, right? The magnitude of R1 minus. And now at this stage, you can say this is G, which is now well defined quantity. The observation you make immediately is that there is no R dependence. Whenever you do not have a coordinate dependence in your Lagrangian, what does that mean? If the coordinate is, if I write the Lagrangian in 3 coordinates, let us say, and one of the coordinate doesn't show up, notice it doesn't show up here, its velocity shows up, but the coordinate itself doesn't show up. So what can you immediately conclude before even you do any calculation?
You say it's a constant of motion.
Exactly. The momentum associated with it will be a constant of motion. Very good. So what you would do is that when you write the Euler-Lagrange equation, you say that first you do dl by dr dot, right? That's your momentum. And then you do time derivative. Maybe I should write it just as P itself. So this is P of R, the various momentums you can define. This is the momentum associated with the coordinate R. And if you recall, Lagrangian, Euler-Lagrange equation tells me that du dl by dr, that's my force. Force is rate of change of momentum is force, but if the Lagrangian is independent of the coordinate, the force is zero. Right? There is no force with respect to that coordinate, so this is equal to zero. And immediately you say that, oh, P of r is constant. And P of r, in this case, is m times dr by dt. That's equal to a constant. That's a velocity of the center of mass. If it's a constant, so what is so special about sailing the whole system with you? You choose it to be zero. You go and sit on that coordinate system and you choose this to be zero. So choose this to be zero. Choose to be zero. Okay, that's it. Very, I mean, it's almost equivalent to saying in quantum mechanics, there is a similar thing. Whenever the commutator of two objects is zero, or let's say commutator of an operator with respect to the Hamiltonian is zero, then you say that the physical quantity there is a constant. It's very good because then that becomes a you can use that as a quantum number. Same thing here. Here you want to look for any quantity that is not present, that coordinate is not present, but it's velocity. That's what you look for. That's a good thing, or that's a very desired coordinate. Okay, so that's your first step. Then you say, in terms of, so once this is chosen to be zero, that's gone. This was zero because it doesn't show up, but then this is a choice. This goes away. And now you're left out with only three variables, all relative variables. You're sitting on the center of mass, and it is a relative velocity that is important. Then you notice that if you were to see angular momentum r cross p, so one can show that the L by dt is also zero. And that's again because you notice that when it comes to coordinates, that it depends only on the radial distance. So it doesn't depend on the angles. So the momentum associated with the angles will be zero, and the momentum associated with the angles is what we call angular momentum. That's equal to zero. So you choose this to be a constant, but more importantly, if you realize that r dotted with L has to be zero. The position, if momentum is a constant, since position is, or if momentum is a constant, since r dotted with r cross p is showing up, r dotted with L will be equal to zero. That means the position is always perpendicular to the angular momentum vector. So there is an orbit plane, which there is a direction, and motion is happening in that orbit. So the motion is in a plane. Are all the planets in a plane, by the way? In the plane? In a plane? Pardon? Yeah, they're mostly similar. Pluto is a little bit off significantly by a few degrees, but mostly they are all in a plane, and that confirms the fact that this is. What if you see a planet that is really not in a plane? What will you conclude? It's what? But yeah, but usually the conclusion made is that did not belong to our solar system. It came from outside. That's a clear indication usually that this is not part of our solar when it was formed. This came from outside and got captured by our solar. And there are comets and objects that come in once in a while. It's very rare that it comes in and significantly outside the plane of the object, and then it's of great interest because it has information about things outside of our solar system. Most of the other things were most probably formed from, or are forming in a sense, they are from some remnants of a death of a star, probably, if there was sufficient time. And again, these are not very well understood things. These are very these things keep changing. Or better way to, we just don't understand the details of it. Mostly it is clear, but we really don't understand complete details, or I don't understand, that's better. Okay, so that's motion is in a plane. Once you have it in a plane, then cylindrical coordinates is good. So we say r phi dr by dt and d phi by dt. Notice the theme is always the same. I'm reducing the number of coordinates. And how am I reducing the number of coordinates? By finding the constants of motion. And this is 1 by 2 mu r dot square plus 1 by 2 mu r square phi dot square and minus of plus g m1 m2 over r. Right. Can we reduce this further to one variable? Is one of these constants of motion? Right, yes, it is, because there is no phi in the problem. So you go further down. So find the phi equation, right? So p phi is equal to 1 by, so it's mu r square phi dot. That's a constant. Call it L of z. And rewrite the equation in terms of that, right? So finally, we have only one variable, so that's r and r by dt now. So just one variable in there, and that's equal to 1 by 2 mu r dot square plus lz square over, so plus 1 by 2 lz square times mu r square. I think that's correct. So r raised to 4, the one of the two powers goes away, and that's plus g 1 and 2 over r. What are the dimensions of this quantity? What's the dimension of Lagrangian? Energy, right? Is this the energy of the system? No, because kinetic energy minus potential energy, right? Because this is the potential energy. So I have to switch the sign of this to show that that's actually energy. And we showed that last time, that energy of the system is, if I switch this, you can start from the Hamiltonian and do the same thing. But at this stage, if you want to show it, you have to actually explicitly show that that is a conserved quantity. And we did show that what we did was we multiplied this with r dot and proceeded to show that this was a constant. That is an energy that is a constant of motion. I won't do that again here, so that we can proceed. So energy is a constant of motion. Oops. Energy. So E is equal to 1 by 2 mu r dot square plus 1 by 2 z square mu r square minus g m1 and 2 over r. And clearly, this is the kinetic energy. In the radial direction, that's the kinetic energy. But kinetic energy has a radial and a phi component to that. This is the contribution to the kinetic energy from the phi direction. But in our way of looking at it, r is the only variable. So it is good to think of this as an effective potential in the radial direction. So we call this U effective, which is a function of r alone. And I should also say that dE by dt is 0. It's a constant of motion. I have not shown that at this point, but we have shown it in the last class. We wanted to do some interpretations. We wanted to rewrite this quantity. So we went ahead and looked at U effective. And if you were to plot U effective, whenever you can see an energy as kinetic energy plus potential energy. Since kinetic energy always is greater than 0, like it is positive, there are some conditions you can right away gather from the energy diagram if you want. So this is the energy diagram. That's your U effective. And for small r, it goes to positive infinity. For large r, it goes to 0 from the negative side. So overall, it's clear that there is a minima. And that minima is used, that serves as a scale in the problem. Right? So in a Kepler problem, there is a radius which sets the scale of the problem. Let's call that R0. And the potential energy at that point is U0. Let's call it U0. In the way I have described here, U0 is negative. So this is a negative number. This is U0 is less than 0, right? Because it is, so this is 0. And it's good to define a few things. What was R0? R0 at this point is very clear, right? Take the derivative, set it to 0. That's how you get R0. And we showed that it was, usually you can get it from here. Just look for the dimensions for R, GM1 M2 times mu over LZ square, or LZ square over mu.
LZ square over.
LZ square, right here. So just check the dimension there and forget that. That's mu times GM1 M2. Thanks. And U0 is equal to, it's half of this potential energy, which means to say that if you, so notice this is the sum of two potential energies, right? If there was only Newton's gravitational law, this would have gone like this. It would have gone down 1 over r potential, 1 over r square is like this. So they together come in. So right at this point, this will be half of this point. So wherever this goes down, that's exactly half of it. So that's the way of looking at it. So this is minus of half of G M1 M2 over R0. Again, that's not proof geometrically, but that's how it comes out. We showed this, what it is. Like again, take the derivative here for the f of effective and find R0 and substitute R0 in the effective. That's what we get. It's also convenient to write this in terms of LZ squared. And help me, is this a negative? I suppose, right? LZ squared over 2 mu R0 squared. Is it correct? So that sets our two variables that we will work with. We will need one more variable, which we will proceed forward and as it comes about. Let me. Yeah, since energy is a constant, we will also find it convenient to define just a constant here, 1 minus E over U0. So that will be a constant E square. If you have seen a Kepler problem before, this will be the eccentricity of the orbit. But as of now, it has not come in immediately. And let's now, using this process of this equation, take stock from energy. So energy is equal to 1/2 mu. We barely started this last time, if I remember correctly. R dot, write it as a chain rule. So dr by dt, introduce a d phi and a d phi by dt. That way, I can work with r as a function of phi instead of r as a function of time. So we're talking about orbit equation instead of a position as a function of time. It's just convenient, and since it is monotonic, d phi by dt is a constant, just dependent on a positive quantity radius. So we can be good that will be fine. Okay, so plus. Let's put this together. So I can write this as so dot square minus G1 and 2. The idea is to rewrite everything in terms of these parameters so that we don't have things floating around, so many variables floating around. That's d phi by dt, that's Lz over mu r square. So that's 1/2. There's a mu square that comes in, kills one of the mu's, Lz square. And divided by r raised to 4, I suppose. And that's dr by d phi square. Multiply and divide by r naught square. This is minus u naught. Minus plus 2 u naught. Well, there is a minus u naught here also. Let's say minus u naught. Let me write it once more. Okay. Minus u naught r naught square over 4 or by d phi square okay, put this all together divided by u naught. That's a convenient thing, and you see this structure coming up. So we have e over u naught plus 1 naught square raised to 4 here on the right hand side, u is gone. So let me say this is, I want to add and subtract now something. So it's r over square plus 2 r naught over r. Add a minus 1 here and plus 1 there. That makes this a complete square. The negative sign taken out. So overall, we get square phi whole square. That's equal to 1 minus e naught. That's e square basically. E square minus, a little bit minus, yeah, minus of 1 minus. At this point, it is not clear what R naught is, so that's visual. picture is not there, but we will in a few minutes get that what it is. It'll be a property of the ellipse. We have to integrate this. So when we are integrating, get everything on one side. So let's take a square root on both sides. We have R naught, R square. Square root, so it is E square minus 1 minus R naught over R. And that's D5. Any questions at this stage? Mostly, like remind, like we did most of this. I think we almost reached here. Last time. It's just reminding of those steps. Integrate this. So let's do an indefinite integral. So we are going along the orbit of the relative coordinates. So if it is an indefinite integral, there will be a constant of, right? And when we are doing the integral, we need to substitute. So let's first of all, the integration constant, we can call that phi naught, I suppose. So let's call the integration constant phi minus. So that's your integration constant phi minus phi naught. And here, substitute. So let me make some substitution. This is 1 minus R naught over R, right? So this is x1, something like x squared minus y squared. So trigonometric substitution sounds good. So let's say this is E times cosine of theta. So that immediately, or first, let me see what this is. I would be able to replace dr, right? So this means that minus r naught over r squared times dr, which is plus now, that's equal to minus of e sine theta. You do that right? Minus. So that means I'm now integrating over d theta. So that's minus e sine theta, d theta over the denominator is e square minus of e square cosine square theta. That's equal to integral of d phi, which D5. The e cancels out. 1 minus cosine square theta is sine square theta. That cancels out. What we learned is that d theta minus d theta is equal to d phi, where theta is a substituted coordinate. Phi is actually the polar coordinate that we have. Theta is a temporary variable here that we made a substitution out of, but they are related in a sense. Okay. So this immediately tells us that we have a relation, right? So theta, for example, theta then is phi minus of phi minus a constant. So it's some integration constant. Trace back, we are interested in r as a function of phi. Right? So wherever we substituted this, if we substitute theta with phi, that's our answer. So as a function of r as a function of phi, which is presumably our orbit, that's 1 minus r over r naught. is equal to E times cosine of phi minus of phi minus phi naught, so it's phi minus. What could be a little picky at this point, when we took the square root here, right, that could be a plus or minus in there. So let's give that option also, so that we have, notice that we have a hyperbola and an ellipse as a solution. So to give that freedom, so let's put that plus or minus. Otherwise, there are other ways to do that. You just have to choose a phi naught. This is an integration variable. Your initial conditions can decide that. Right? You just have to choose this phi naught appropriately. So that gives it. So no, that doesn't actually. No, I said it wrong. I don't think the initial conditions can decide your energy. The whether it is an ellipse or a hyperbola is decided by how much energy you have, and the energy content is there in the eccentricity. So which orbit the system goes in is decided by these variables. So there's R naught and E, these are the two variables. Relatively, how much is U naught with respect to E, right? If this is greater than 1, there is something, less than 1, there is something, if it is equal to 1, there is. So this condition is important. So E decides what kind of orbit you have. And so phi naught initial condition doesn't do that. Initial conditions decide your angular momentum, and that can decide your radius, how far, how big your scale of the orbit will be. So that's it. Okay. But that's our solution in principle, right? R as a function of phi. So let me rewrite this as R, and so I'll write this on the left side, and I said I will set plus or minus, right? So there's a plus or minus. So R as a function of phi, that's my orbit, equation of the orbit, is equal to R naught divided by 1. It came out minus, but I argued that it can be both plus or minus, so that's cosine phi minus phi naught. That's not very informative, right? Or is it? Like, is that a familiar equation? That's our orbit. R as a function of phi. It's a solution, and apparently we call that an ellipse. Right? Is that an ellipse? Have you just come across this before? So, what is the equation of an ellipse? If I were to ask you guys more familiarly, like what do you remember here and there, something like equation of the circle. What's the equation of the circle? X squared plus y squared is equal to constant. What's the equation of an ellipse? Right, so that's how most of us remember it like that. But what is this then? This also I say is an equation of an ellipse. So x squared plus y squared, x squared plus a squared plus y squared plus b squared, where a and b have meanings of major axis and minor axis. This is in rectangular coordinates. But now we are working in cylindrical coordinates. So cylindrical coordinates, that's in cylindrical coordinate. This is cylindrical. But then that should be connected, right? They should be connected to each other. But what is it? Let's go back and look at ellipse itself. How do we define an ellipse? Go back and how do we define a circle? Very elementary ways. If you have to teach someone, some middle school student, what's an ellipse? How do you, or how about a circle? So the ellipse is
Conic section.
Oh, conic section. Yeah, that's very good. Let's go simpler. Circle, like not an ellipse. Maybe you are answering ellipse probably, right? No, circle, I'm saying. How do you explain a circle to someone? Someone from middle school has not seen geometry much.
If every point on the circle is the same distance,
Same distance, right? First decide a distance, decide a point, and all other points which are equidistant from that, right? That's what it is. Math department, UREC, right? Kochik, Dr. Kochik, he says, and I think he was really trying to convince me that in olden days, we had animals, you tie an animal to a point and it grazes grass, right? And you see that there is a region which is grazed out, and that will be a circle. So his point was that this really came out of the historical event, but it's clear that you have a point and it is equidistant. But what about ellipse? Like circle is easy, right? Circle is clear. It should be clear to all of us that this you pick a point and equidistant. It's called the locus of loci, right? Loci of all the locus of loci of all the points that are equidistant from another point. So what about an ellipse? There's a similar definition for ellipse. What is it? Which is very, very much like something equidistant. No? But have you seen ellipse being drawn? How would you draw a perfect ellipse?
I know that you can
Yeah.
take 2 push pins
Correct.
and then a length of string.
Correct.
And so basically the overall, I mean, that string is a constant. The length of the string.
Exactly. So that's the constant. So what Rob is saying is that first pick 2 points. Here there was 1 point. Pick 2 points. Right. So here the idea is that you took a goat, let's say, and you tied it to a point, and how far you can raise it. Now let's take the same goat, but now now it has to be flexible somehow, right? So there is a string. So the idea is maybe not a goat. It's not a good example. Think of it. Shape. So this is a string now, which is larger than the stretched out region, and now you stretch it. Take a pencil, stretch it out. Right? In each direction, there is a maximum limit in which you can go. And if you were to draw this will come out to be an ellipse. Is that clear? Maybe you guys have seen it. Otherwise, look it up. Right? Or quiz, draw an ellipse. Why not? Yeah, draw an ellipse. Okay, so we have this point here. There's this point, and that's your ellipse. Not bad. Not a good one. Okay. These 2 points, this is the center of the circle. These 2 points play an important role. That's called the foci. Foci is a plural, right? Yeah. Two focal points. They are equidistant from the center. Now notice that when you think of rectangular coordinates, that's xy. When you're talking in terms of this equation, that's in terms of that xy, and this is your coordinate system. Right? That's my x, that's my y. Right? When I say I'm interested in the polar coordinates, you change your mind. You don't want this as the origin anymore. It is with respect to one of the focal points. And for reasons you will see, it's just a choice. I can choose either one of them as the origin. I choose the right side. So that's my R. And that's my angle phi. Is that clear? So you move the origin now. It's no more the same origin here. Okay, so if that's my distance R, let me write that here smaller. There's another distance from the other focal length, right? So that's C is it. This distance here is my definition of focal point, focal length, so it's F. Focal lengths are equidistant from the center of the ellipse, so that's F. And there are some more definitions. So this is my major axis. That's my minor axis. Clear? By saying that this is a fixed length, what I mean is R plus C. R plus C is a constant. Right? That's a definition of ellipse the way Rob was describing. What is that constant? That's a constant, so it should be true for any point. So let me take this, bring this point here. Right? At that time also it's the same and it's a constant, so I just have to know what that is. So this line, when it is at this point, it is, this distance is A plus F, and when I return back, it is A minus F, right? So this constant is R plus C is F plus A. That's when, that's a C part of it. And the R part is A minus F. So it is A minus F. The F cancels out, so this constant is basically 2 times A. So we have learned that R plus C is equal to 2 times A. We still want to process this information. This is a triangle, right, whose one side is 2 times F. So if I were to draw that, so separating here, so that's 2 times F. C, that's R, and that's phi. That's a triangle. Use the cosine, law of cosine, right? Law of cosines there. So it is C square minus R square minus 2 times F square is equal to 2 times F times R times cosine of the angle that is opposite to C, that is 180 minus phi. Cosine of 180 minus phi is cosine of phi itself, except that it here brings in a negative sign. And let us replace C with 2A minus R, so that I can get rid of that unknown quantity. And then everything is in terms of F and R. So it is 2A, so now I can, so this is 2A minus R whole square. And so let me save a step. So let's expand it in my head. So that's 4A squared plus R squared minus 4AR minus R squared minus 4 times F squared. So equal to 4FR, and cosine of phi, but with a negative sign. The R squared cancels out. And what? Well, 4 cancels out. Everything else, 4 cancels out. And that is A squared minus F squared. It's equal. Square is on the other side. And yeah. A times R minus R times F cosine phi. Okay. I'm interested in R. So R is equal to cloud and A. So it is A square minus F square divided by A over 1 minus F over A times cosine of phi. That way you can match with this. That will help us understand what R naught is. Okay, almost there. Let's do one more definition. E is going to be, let's define this as F over A. So there are two definitions of E. We'll see that it's the same. Let's just actually you can read it out. Yeah, you can compare this and right? And let's also say that yeah, okay. Let's see. Okay. So when I brought this down here, I got this condition. The same string can be put here, right? So right there, at this point, I have a condition. This is my focal point. This is my distance B. And this distance here then tells me that this is B squared plus X squared. So this is B squared plus X squared. And that's also equal to, if this total distance was 2 times A, that's also equal to A. When I'm right at the top here, this total distance is 2 times A. When I'm going this way and this way, the total distance is 2 times A. So one of the distances A. So that's my A, which using a right triangle law should also be B squared plus F squared. So that gives us a condition between E squared. So this implies that, E is actually equal to, that is my E, is F over A, F squared over A. So 1 minus B squared over A squared. And this is how, since often we come across ellipse from the rectangular coordinates, it's easier to see it in terms of A and B. Then you define your eccentricity as 1 over B over A, but it's basically the same idea, different parameters. Now, in terms of that, so B square, A square minus F square, right? That's your B over A, and I will define my distance. Okay. We define a distance. Okay. Let me call this R now. How about that? So this is your R. Again, comparing this with this, R naught over 1 minus E times cosine of phi, and my R naught then is equal to A square minus F square over A. But there's an easier way of looking at it. Now that we have our coordinates, let me set at what point does R exactly become R naught? At what angle does R naught become the actual point on the, or actual radial coordinate on the ellipse? I need the denominator go to 1 then, right? Phi half, right? So phi is equal to phi half, 90 degrees, R is exactly equal to R naught. That gives me a measure for R naught immediately. So look at my orbit, that's my ellipse. My focal point is here. When this is my R phi, right? So that's my R and that's my angle phi. But there is a point when I'm making 90 degrees there. That's my R naught. Okay. So here is it. So there was a quiz for you guys that in Kepler's law, what distance plays a role? Is it the radius or is it the semi-major axis or so on? It is R naught over this quantity that comes in. There is a eccentricity also plays in. It is 1 over E, but I'll put that as a homework exercise or somewhere I'll ask you guys. So, but now you can investigate that. So the idea is that now in all these parameters, now that you have R, yeah, what's the time period? We haven't yet decided that. How will you find the time period? Right? You will go from phi equal to 0 to 2 pi, right? Integrate over that, and this integral is doable. So if you integrate from phi 0 to 2 pi, right, you can get how do you do this? What was I saying? Sorry. There's one more thing you have to do, right? Yeah. So this is R. So we have d phi by dt, correct? We want the time. So d phi by dt is Lz square over mu r square. Correct. That was your conservation of angular momentum. Substitute this in here, R. Right? R gets substituted here, and then you integrate. So your dt would be equal to d phi times mu over Lz square times R square, where R square will be R naught square over 1 plus or minus whichever orbit you're doing cosine phi square. Is that clear what I did? Sorry. Start from d phi by dt, write dt as d phi times R square in the numerator, and that's the integral you'll get. And go from 0 to 2 pi. And this one you say goes from 0 to t. Right? That's the definition of time period. This integral is doable, and whatever you get as a result is your Kepler's third law. Right? This gives you Kepler's third law. I'll ask this in some form somewhere because it's relatively easy to do. So there's only one place I can ask. There's only one point remaining. So you know what it is. Okay. So that's your R naught. Here is a quiz for you guys. Remember, so what is this point? When does that happen in the year? Let's say sun is here, right? That's your sun. Where is January and where is December in this? These two are called the perihelion and ephelion, and these 4 points represent the longest day of the year and the shortest day of the year. And this is the 2 points where everywhere in the world it's the same 12-hour distance. Right? At this point here, everywhere in the world, the daytime is the same. That's interesting. So this is, it depends on whether you're on the south hemisphere or north hemisphere. It's the longest day or the shortest day, and the opposite in here. Now, this is happening, let's say either the September or March, right? Whether you pick this or this. So this is either September or March, one of those days, whenever the it starts swinging, the day starts getting longer instead of shorter. So there is a switch that happens. And this is also a special point from our perspective, because that's our R naught, right? And the question is, how far are these 2 points? Okay, so this is the quiz for you. It's don't try to do this exactly. You can in principle. I've given this as a homework. You can do this as an exercise starting from this equation alone and analyzing it. That's probably a little tedious. If you go back and look into my lectures, you'll find it. But what is interesting to ask is that how far are they? Remember, the hint is that how much is our E for Earth? I think Rob, you said that I think 0.01, I think, right? That's about approximately 0.02, I think. It's really tiny. That means this ellipse is not significantly off from the circle. And geometrically think that what happens if it is not really significant, you bring this closer. It's not really very off. But if you can get an estimate, just hand waving, that's good. It's a whole exercise I should find out, but I don't try to spend too much time if you don't have the.
One of these points that you said that day and night are the same.
Yeah, it is 12 hours and 12 hours. Yeah.
One of them is on here.
Oh, that's it. That's the one that just passed away, right? Oh, that's a good point to choose. Yeah, a lot more scientific. but most probably, yeah, many of the days are probably right. Yeah, good point. Yeah,
they call it spring revolution.
Spring revolution. So that's revolution, you call it. Okay. Good. Yeah, nice. Okay, good to know. Now I'll remember it. It's easier to remember now. Okay. Good. What else to say here? Oh, yeah. So here, notice that the way this went about, this was just coordinate geometry, right? It was necessary that, oh yeah, I can say, yeah, what about this distance? This is the closest distance, right? This is R minimum, right? And there is an R maximum, right? And that's easy to do because phi equal to 0 gives me R minimum, right? So R minimum is R naught over 1 minus E. The sign of 0 is 1. And R maximum is R naught over 1 plus E. So that's another 2 variables you can bring in. And that actually should let you choose this point here. Is it plus or minus? It's clear that this is, we have chosen E to be, if it is an ellipse, it is 0 to 1. It is between 0 and 1. So the focal point is smaller than your A, right? So E was F over A, so that's smaller. So let's go back and look at our definition. We defined E in another place also, right? So that was your 1 minus E over U naught. So let me do that also. So I'm waving here. More organized. So you have E is also equal to 1, or E square is 1 minus E over U naught. Remember, U naught is negative. U naught is already a lot less than U naught by definition or construction was negative. But so if I want this to be between 1 and 0, that means I also want E to be negative. So this implies for an ellipse, E has to be less than 0 and greater than U naught. Like remember, U naught is a negative number, right? So it's 0 and a negative number has to be in between that. So in principle, even though this looks like this 1 minus E over U naught, it's a little confusing. Because first you argue that it's U naught is negative, but then you have to come and say that E is also negative. So otherwise it's easy to confuse that, oh, this is a positive number because U naught is negative. But then you say that energy also has to be negative. So be careful about that. And of course, that leads us to the idea that what if, so this was your R, that was your U naught, that's your R naught. And the total energy, when it is somewhere here, E somewhere in this region, that's an ellipse. Exactly at this point, by that I mean when the energy is in here, that's my circle. When it is down here, that's parabola. And we are not talking about any of that. I mean, all this analysis that I did, I should restart the whole thing for an hyperbola, for a parabola, and so on. And we should investigate where exactly is the particle in the orbit. And that is done usually. And the best book, or I shouldn't say best, right? One of the books I have found, this is pretty well described in many places. One of the books that did this quite early is Landau and Lipschitz. And I think many books follow that also, but it's a good, exposure. So this is hyperbola. So for other curves, look up the reference there. And with this, I will stop. So now what we will do is all this is two-body problem, right? We began with M1 and M2. And the easiest thing you can do is that keep everything, you want to keep many of the properties the same, and you want to perturb this very little bit. Right? Say that there is a tiny perturbation in this interaction energy, and then still use the equation as much as possible, but as a perturbation. And we will do that, and that will explain the perihelion, precision of the perihelion to a good extent. Okay. Thanks. So this was the application of the whole semester. This was, in a sense, an important lecture.